Okay, I'm just happen to be recording right at the moment. So you've built a balancing robot.
Yeah.
And I hear a high-pitched whine. Is that the PWM?
Yeah.
And so it's pretty good, although it has a tendency to run away a little bit.
Yeah.
Do you think that's because of the wires on there?
The wires definitely have something to do with it, but it's just also it's just a limitation of our design because we didn't include wheel encoders, so we can't directly measure the speed of the wheels.
I see.
If we had wheel encoders, we'd be able to have a two-layered PID controller, one that controls the tilt of the robot based on the speed, and one that controls the rotation of the wheels based on the tilt to maintain balance, basically. But since we didn't do that due to cost reasons mainly, we have to rely on just hoping that the robot doesn't accelerate too much and that the wheels saturate. So if it stays within a reasonable speed, it could perfectly balance.
Well, it's doing pretty good. It's looking pretty good. So the counterweights on top are batteries?
Yeah, they're batteries. They're just the most convenient ways that we've found.
Okay. Oh, so that's not part of the robot. It's just...
Yeah.
And initially wanted to balance something on this right here. Hopefully balance a cup of water.
That's asking a lot, yeah.
Definitely asking a lot, because you can see it just bobbling.
But it's, it's being pretty stable there. It's doing pretty well.
Yeah. So basically, we have the 12 volt, or basically a 13.5 volt power supply over there that's supplying to somewhere around like 3.5 or 4 amps, and that's specifically for the motors. And we have a battery. We have nickel metal hydride. We have nickel metal hydrides batteries here underneath are powering the PIC32. Therefore, so that it's completely isolated from the motors, because we realize if we connect it to the same power circuit, then
it's going to turn on.
Yeah, then we have. If the motor requires too much current, a lot of times the PIC32 completely powers off because it's not able to get enough power.
It's very important that we opto-isolate the system. Nothing functions without it. And
well, that's right. And
I would say that I thought we could get away with it by connecting the grounds, and from testing, that's just not possible, especially at high speeds.
With the big motors like that,
big motors, you're not going to get away with that.
That's right, and that's a big lesson that. Always use opto.
Yeah.
That's the.
So yeah, these are our opto isolators here. So the PIC32 directly, does pulse width modulation on 3.3 volts. And then the opto isolators take 5 volts that's actually coming out of the motor driver, and then amplifying the PWM to 5.5 volts after the opto isolation, sending it back to the motor driver, and then the motor driver is amplifying that to 12 volts, sending that to the motors.
That's a dual H bridge. You got it.
Yes.
And also one thing to notice is that the resistors connected to the port pins are different. So these two resistors are the same, and these two resistors are the same.
And that was, you had to do that to get the turn-ons to be reliable.
This was mainly because the wheels had different RPMs. They were not the same as we thought, and because we needed to oil it for the most part, and to mitigate that problem, we had to change the resistors. To control the speed.
Because you'd think with a PWM system it would either be on or off.
Yeah.
But that says that there must have been just a little bit of analog effect there. There must have been a little bit of...
Yeah, just like if the motors were spinning without any load, it was pretty clear that one motor was spinning slightly faster than the other one.
And that fixed it. Changing the resistors fixed
that. Fixed it to at least for it to work with this.
Yeah.
So let's say you are...
Interesting. I have no idea why.
In terms of the balancing itself, this is an MPU 6050 IMU, and basically it's a 6-degree of freedom IMU. It has accelerometer and 3 axes and gyroscope and 3 axes, and the PIC32 is reading this via I2C at 20 hertz, basically 20 times a second. It's reading that, and then we have a we have a sensor fusion algorithm. It's called a complementary filter that takes the accelerometer values, passes them through a low-pass filter, and takes the gyroscope values, passes them through a high-pass filter, basically, and then averages and then integrates the gyroscope, and then averages the two values together to basically get as accurate a tilt measurement as possible.
Okay.
And then it takes that. Then it takes that as the feedback for the PID feedback.
Cool.
And we had to go through multiple iterations of filters. The first one we used was the IIR.
Yeah.
Then we had to just reach to complementary. Ideally, go for the common, but we all know it's very complicated, and we just didn't have time to.
Right. The Kalman filters are nice, but also sleep is nice. Mm-hmm. Yeah. Okay.
From looking online, they refer to it as the magic.
And finally, to make the user interface as convenient as possible for debugging, we added the LCD display here that displays a bunch of statistics about what's going on with the robot right now. So the top right here is actually measuring the absolute tilt of the robot in degrees from the vertical. The second one is measuring the gyroscope measurement right now. So if it's steady, then it should measure 0. Mm-hmm. And then these are the PID coefficients. So technically, what we're using right now, these are controlled by the potentiometers here. You just twist the potentiometer to change the PID coefficient. So technically, right now we're only doing a PI algorithm, because we with this particular configuration robot, we realized that the D term doesn't really help that much.
And the potentiometers are then read by the ADC to set the. Oh, that's handier than using a typing interface, isn't it?
Definitely.
Yeah.
It allows very frequent, very rapid iterations to tune it.
Okay. All right, thanks.